Okay, welcome everybody. Some of you may have come to us via MMP, some of you via the Royal Society, some of you are on the NRICH mailing list. So quite a diverse group of people. Welcome to everybody. We will be telling you a little bit about MMP and two of the projects of the Millennium Maths Project, Plus and NRICH, who had the pleasure of collaborating with Julia, Professor Julia Gog, here at the University of Cambridge, who decided to use the grant money that she was given for the Rosalind Franklin Award to produce resources with us for school-age students, Key Stage 3, sort of 11 to 14-year-old, about how maths supports understanding of the spread of diseases, which is what she works on. And I'm going to invite her to tell us a little bit more about the work that she does and the award, and why, Julia, you chose this project to be the one that you were going to dedicate your energies.
Got it. Thanks, Charlie. And thanks everyone for joining us, whether you're joining live or joining the recording later. And thanks, NRICH, for hosting me on this. This is fantastic. Every time I think about Contagious Maths, I smile. It's just been a wonderful project, and we hope we can share some of this fun with you today in the webinar, and our enthusiasm for this. So my day job is I'm a professor of mathematical biology. This is my very, very messy office here in the Centre for Mathematical Sciences in Cambridge, where I'm based, which is along with MMP and NRICH and Plus. We're all in the same mega department. My day job is modelling the infectious disease dynamics, so looking at epidemics, and needless to say, I was rather busy during COVID-19 times. But I've always had an interest in sort of sharing the research with the outreach and communications, and that started with MMP years ago, working with the Motivate project, which was for video conferencing for schools some, 18 years ago? Can you imagine that?
Well, I had a look, and apparently 2005 is when, so 19 years ago now.
19 years. Who'd have thought to communicating to schools via video conferencing would be a thing? But things have moved on since then somewhat. So this brings us to the Franklin project. Our sort of code name for it has been Project Franklin internally, because it's been funded by the Rosalind Franklin Prize from the Royal Society. It's a lovely prize from the Royal Society, but it brought money with it, which is grant money, which has enabled us to do this project and put it together. Yeah. Well,
it's been a great opportunity for us to work with other members of the Millennium Maths Project in a way that we haven't done before. And with you, a researcher, member of the Faculty of Mathematics here. So it's been a new collaboration, which hopefully will help children and teachers and the wider public appreciate how maths is being used and applied.
Yep.
Presuming that was one of the reasons for choosing this as the project to...
Absolutely. So bringing an interesting research idea to a school's audience directly, rather than it filtering through lots of different layers, just go for it directly. And maybe we can talk more later how that applies more generally and what that means for mathematics.
And the decision to do this came before COVID.
Long before COVID. So it was, lots of discussions with folk in MMP, including Ems Lord and Julia Hawkins, and thinking about what can we do with research to put something together which engages school audiences, and in particular girls. And that made us thinking about bringing real world applications. And so, wait, what do I do for a living? I do epidemics, which has real world applications. That's where it all came from.
Okay. So we've produced some resources, which we'll share with you and so on, but perhaps maybe demonstrate one of the resources straight away.
Let's get into it.
Just to get everybody, give everybody a feel, a taste of what we've produced.
Right. Let's just have a quick tech check. Is this looking okay? Okay, you can kind of see us and this at the same time. Brilliant. Okay, so we've got the lucky dip model here. So this is a simple model for an epidemic. You've got the generations across the bottom, G1, G2, everything starts generating 1. And let me just show you one generation, and let's go from here. So these are 26 red balls going into the tombola, which I think NRICH uses for other things as well, the tombola. And one comes out representing the first person infected. And the way we're going to run this model is each person infected is going to pick 2 others to try to infect.
And it's called Lucky Dip because before we had the interactivity, you've represented this with a bag and 26 balls or red cards or
red tokens. And actually, I don't know if it'll show up on the camera when I put it in front of my face. I actually have one of the actual tokens used in the original run of it, which is
from the Royal Institution Christmas Lecture.
Royal Institution Christmas Lectures 2021. And it was literally Lucky Dip then. It was a giant bag.
Yeah.
So that's why it's still called Lucky Dip model.
Right.
So, but this is an online version. And when people are using this in schools, you can just, you don't need to get the huge bag and the thousands of balls. It's right there. I'm pointing over there, actually. Is it the right place in the screen? No, it's sort of there in the screen for you. And it's there and online interactive. And I should say the lessons don't start here for the teachers and the students. This is halfway through lesson 2 we're piling into.
Yes, and we'll show everybody the whole structure. And the 2 there, that what does that represent?
So you might have heard of R, sometimes badly called the R number, and you know that sets me off. But R is the number of people that one person infected would go on to infect.
Okay, so this one person that's been pulled out of the bag is going to return into the bag and have the opportunity of infecting 2 other people in the bag.
Yep. Should we see how that happens?
And there are 26 people altogether in the bag because
Correct.
we used to do something with red cards and black cards, and there are 52 cards in a pack, so half of them are red and half of them are black.
Yep, that's exactly it. It's a number of red cards in a pack because it also works with cards.
Okay, so there's no really good mathematical reason for choosing 26, but that's the history of it.
There's a side story. We looked at all sorts of numbers for Royal Institution, and we actually did modelling. You know, of course, I simulated it, coded it up and ran it rather than getting lots of bags. And we ran all these different numbers to try and work out how many do you need to have a decent size epidemic, so it looks like an epidemic, but not so it takes forever to run. And 26 was in the sweet spot anyway, so we lucked out the first time. So it's our lucky number for epidemics.
And it means people can use packs of cards and red cards and replace them with black cards if the need arises when.
Yeah.
Okay.
Once you understand the model, it's not too hard to see how to turn that into a card run model.
Yes. Okay,
ready?
So go for it.
Run one generation. Okay, that's the empty one going back in. They're going to be recovered later, but first they're going to infect 2. Dun, 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 dun. There they go. 2, right.
And they've got 2s written inside them because that's the number that they are going to go and infect when they go back into the bag.
That's right. So each is going to attempt to infect 2. And they're going to
attempt to infect.
Well,
it makes them sound rather
it sounds like
weird or evil.
It sounds like some bad game of tag or something, but that's, you know, it's a model. It's a model. It's not real infection.
Okay.
And that's it now. Oh, it's built. That's the graph building up. Okay. So we've got 1, then we've got 2. How many do you think we're going to have next?
So the first one is no longer infecting anybody. It's the most recently infected. So they'll go back and chances are that they'll each infect 2 more.
Let's find out. In they go, 2 empties going back in. Dun, 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 dun. Oh. Oh.
Okay, so what's happened there? 3 of them are going to go back into the bag at the next generation and are likely to infect others. But one says that they're immune. So they came into contact with one of the others who were infecting, but they were immune. So presumably it was the one that had been infected in the first round?
It must have been the very first round one. So so it's one of the capsules was pulled out, it was empty. That's what the little sort of lack of 2 in there is. Yeah, so if they're empty, we're going to model that as meaning they're immune. They've had the disease, and we're going to take the assumption they can't get it again.
Yes, that seems fair enough.
It's how most diseases work. Not all, most.
Okay.
Okay, so
So what does the
next.
graph look like?
Well,
1, 2, 3.
Unexpectedly 1, 2, 3. Actually, 1, 2, 3 is kind of rare. It's normally 1, 2, 4. It's a spoiler. Okay, but we've got an interesting one. Okay, let's see what happens. So how many are we going to pick out this time?
So it may not be 6 because there are going to be more
Oh, no.
immune people.
No, we're going to pick 6 capsules.
Oh, yes.
But how many are red?
Ooh,
Oh, we know.
all of them.
All right. So all 6 get infected. All the 6 were new people.
Yes, they had not been infected before. Okay.
So that comes up there. Oh, that's going to get big quick. What's going to happen next?
So we've had 1, 2, 3, and 6. So something like 12 already now immune. Chances we're going to hit a few more immune.
So you're thinking about the population of 26, what's actually in there?
Yes.
Yeah, quite a lot are immune. There, okay, so
I think you can scroll down and
yeah.
see. Okay, so a few immune. So 9 were new infected people.
Yes, it looks like that. So let's have a look at the plot. Gosh, right, that's getting tall. Let's check that's showing up
So
okay.
nearly everybody has been infected now.
You're faster than me.
9 and 1, 10, and then we've got 6, 3, and 2. I think 21 possibly.
I mean, it looks a lot like
Very
21.
few have escaped this disease.
Oh, okay, so we can put an upper bound on number infected next go. Let's find out. I click next.
Maximum of 5.
I click next. Will it click through faster, or should we let it go? Oh no, it's there anyway. By the time I thought about it. Oh, is that 5? 4. 1,
2, 4.
4 got infected. All right, so that's the 4. We know there's just one red left.
If I've done my sums correctly, I think it may just be 1.
Let's find out. Okay.
Yeah, I can see at least. Yeah, I can see
there it is rattling around. Is it going to be picked out as one of the 8? Oh.
So the infected people only came across people who were immune,
Yep.
who couldn't be infected again. And it looks like one person, if I've done my sums correctly, has escaped.
Yeah.
Just by chance. They were lucky, not because of their diet or their, well,
who knows?
Yes.
But it's if you can imagine it in a bag, it's sort of very visual. There's nothing different about the ones that are in there. You'll have to trust that our colleague Oscar has coded this up beautifully, and I'm quite sure he has. So there was always the chance that one would get infected. It could have been picked at any step.
Yes.
Just got lucky. An epidemic ended before getting everyone. That's one model anyway.
And like we said, this was quite early on in terms of the series of lessons that we've organized. Shall we go back and just look at where everything is and how it's been organized?
Well, shall we jump back? Should we have a look at the overall landing page and then sort of navigate from there?
Actually, it just occurs to me that one thing that we haven't done is look at what happens when the R value is not 2.
Oh, we can do that here. Okay, so if you look at the top right there, there's the amazing purple cog. I click that, that gives you on all of these activities, I think on all the NRICH activities actually.
It's always, yes.
It's always purple cog, and it gives you a chance to change things. So we had 26 for reasons that are close to my heart. You can have 50 or 100. Remember that's a number that was being pulled out, the number of infected, so that you can make that 1, 2, 3, 4, or a random 0 to 5. And you can have, rather than just the simple plot, you can have more things, which I think will let people explore on their own. But you wanted to try a different R. What do you want to try?
Well, one might be a bit boring, mightn't it? Because you every time you're infected, you infect one other person. So that would be fairly flat until you infect somebody who's already immune, and then the whole thing comes to an end.
Yeah, there's only a few things that can happen. The question is, how long does it go on for, of course? And there's some interesting maths to be done and explored there.
Yes, because we could work out an average. We could run it several times and
see if it fits what you expect.
Yes. And R3 might be quite steep to start with.
Should be pretty, R equals 3 is pretty bad news if you've got that in a real disease. So I'm going to next that one. So we've got our first one.
Yes.
In fact, there's a button here to run to the end. So if you want to skip the animations,
Yes.
Are you ready? This could be quite explosive. Oh, so much so it went off the screen. So it went 1, 3,
8, and then 13. So
then it collapsed to 1 because obviously it's.
Well, 8 and 13 on their own add up to 21, and then another 4. So, it looks like maybe everybody got infected there.
Let's see, 8 plus 13,
did you have
21.
Did you have 26 or 50?
26.
Yes.
Oh, yes, that was a total wipeout one with the R equals 3. I wonder how often that happens.
Yes. So very quickly.
Very, very explosive. And if you do R equals 4, it'd be even more drama.
Okay.
So the higher R values are really, really explosive. The lower ones, here we can only do 0, 1, 2. 0 would be a very boring simulation, so that's not an option on the purple cog. 1, 2, 3.
Yes.
But R equals 2 is already a pretty, it's almost doubling every time to start with.
And the nice thing about running to the end is students can do this many, many times and compare the different graphs.
That's right. So the sort of question is, we're already thinking about how many were left at the end. You can explore that and see, is it actually quite often total wipeout, or sometimes 1, 2, 3? Can you get more than that left? And this one was actually very short with large value of R. The epidemic was over. Generation 5 was the last round of infection.
So we had almost a total wipeout with R equals 2. I mean, we don't know that that was typical.
Not yet, no.
Because we only did it once.
Yes.
But is it more typical to have a total wipeout with the higher values of R? Yes.
And my mind's jumping to the research maths. We've got some beautiful results about expected number of people left at the end of the epidemic. There's some lovely degree maths.
But that's the question that students could be asking themselves and trying out. And
yeah, absolutely.
Different students in the class could be testing out different values of R.
Yep.
Maybe with a greater number of population of 100 rather than 26.
I would go up to 50 or 100 for those explorations. You get sort of more interesting distribution at the end.
Yes. So nice statistical analysis. Because part of the criteria for choosing the activities was that it was going to be linked to school curriculum that teachers and students might work on in class, and being able to compare the numerical results and the graphical results, make predictions, conjecturing, explaining, all part of the national curriculum in the UK, no doubt abroad as well.
That's
Good.
right.
Yes. Okay. So shall we just look back at how we find where did we start from?
Let's get rid of one of these. So a couple of people were asked, are you going to have the recording afterwards? You're going to have an email, I think, with links as well. So don't worry about trying to grab the URLs immediately. But the overall landing page for the project is on the Millennium Maths Projects page there, at maths.org. And it's
maths.org, I think, /contagious-maths.
Yes, that's right.
And on the NRICH side, it's nrich.maths.org /contagious-maths.
And what is it on the plus side?
And it's also something like plus
same.
something /contagious.
It's all the same.
It's always the same on all three. And everyone will get an email with all 3 links so that you can access the resources by whichever sort of route you're used to. So if you're used to going to Plus, you'll be able to find via Plus.
Yeah.
The Millennium Maths Project link might be
I think
the
this is the best one to start with because it introduces a little bit about the project and it gives you the two other routes straight away.
Yes.
So the resources are similar, the videos are similar, the interactives are similar between the two, but we've designed it in two ways. This one on the left is the enriched version, which is designed for use in classrooms. You can use it in a sequence of lessons. This is the one we're going to focus on. And Charlie, we're going to talk about the teacher notes as well. This is the Plus version. This is designed for someone looking at it on their own a little bit, to like an older student or any member of the general public. And actually, for teachers, if you want to explore this a little bit more before you use this, one way to get your head around it a little bit more for yourself is to go through the Plus version first, I think.
And in the enriched version, there are teachers' resources, and we've put links to all the resources that the Plus team have been publishing to support teachers who may not be very fluent with this maths.
This one's the left-hand one, the enriched one is designed really for the teachers. There's me. There's me and me. Look at that. Me a few months ago. There we go. So that's introducing a bit about the project. At the bottom, you've got a little bit of the about, which tells you about the Rosalind Franklin Award, and that the RI Christmas lectures were an inspiration. And it's you've got Charlie and I presenting this, but there's a whole team behind this that have written and developed these resources. You can see all that. It's the Plus team, it's the enriched team. We've pulled in basically everyone from the MMP to do something on this. And I guess the reason why this is quite special to us is the Plus, the people who are normally used to Enrich maybe don't know so much about Plus. And it's the Maths Communications Unit, which links very directly from researchers, really cutting edge research, big news and research, through to the general public. You guys in Enrich have the ability and skills to communicate directly with schools, how you can do enriched maths in schools. And then you've got me as a researcher who wants to communicate these things, but maybe I don't have the same expertise. So you've got the connection through Plus and Enrich to bring the whole shebang to a school's audience. Yeah. It's been fun.
Yeah, it's a great opportunity.
Maybe we should highlight now on this. If you use these resources, this is a bit terrifying for us. We're just throwing these out into the world and hoping this works for you and you can use these. Tell us how it works. We really, really want feedback. So even if you've just used them and it worked fine, you haven't got much to say, please drop us an email via that link. We just would love to know they've been used.
And I've also put a link on the teachers page.
Perfect. Okay.
Which we'll come back to.
Great.
I just wonder whether we should show them the sort of follow-up interactivity and why we've got a follow-up interactivity.
Oh, yes.
So
we get to ask the teachers to do some work first, though.
Okay, so what we're in the teachers' resources, we suggest that students might want to think about what were the sort of deficiencies of the original model. We were using the lucky dip model, where one person started being infected and was always infecting either 2 or when R was equals to 3 people, and then they were going back into the bag and so on. But we've got a follow-up model which we think is an improvement on that. But what we thought we might do before introducing that is ask students to suggest what are the deficiencies of that model. And we thought we'd invite everybody to contribute in the chat.
The wording, what else do you think should be taken into? Actually, I'm going to stop share, but that's what we're going to do, is that bit essentially there. So if I stop share, then you can actually see us a bit more clearly. This has been recorded, but I think what you type in chat is not. So don't be afraid of putting anything there. That's absolutely fine. Question we've got for you then, and we want your answers in the chat, is I've shown you a simple model of an epidemic here. You can see it's there about sort of counters and capsules in a bag. In some sense, it represents a real epidemic, right? But I want you to criticize it, right? what's missing between that and a real epidemic? What else could be in the model to make it better, to improve it, or what just is completely different from reality? Please just, what are your thoughts? What's lacking in the model? And just, you can imagine what your students would say, or you can just answer what you think. Oh, yes, great. Great. Okay, maybe I should start talking about the ones we've got. And please keep putting your ideas, and there are no bad ideas here. There's lots wrong with this model that you can pick up. So the very first one there is non-integer R.
Yeah,
that's a great one.
We jumped from 2 to 3.
Yep.
And didn't consider that R might be somewhere in between.
Yeah.
Okay.
That's okay. That's sort of limited by the capsules. You know, you've got a capsule. How many are you going to pick? What does it mean to pick 2.5?
Yes. So the first interactive model sort of reflected what you did in the real context of having a bag with some real capsules. Okay. So we hope the next one might give us a little more nuanced, a more nuanced model.
Well, maybe if I was teaching this to a class, I'd ask them what it meant for people. If you had an R of 2.5, you're infecting 2.5 people, and bring around to the idea of course, R is an average, right?
It's a bit like the average family size might be, or the average number of children being, I don't know, 1.9 or 2.2 per family.
Yeah. So for a given family, you shouldn't have non-integer, but when you talk about the average, it will be almost certainly non-integer.
Somebody has mentioned that we haven't taken into account the effect of vaccination.
Oh, well, you'll enjoy the next one then. That's right. So we just simply had the disease, and people were only getting immune by capsule being opened, the counter taken out, and going back in. Actually, this particular model, you could adapt it to have vaccination just by deciding, okay, I'm going to start the simulation again, but I'm going to have some of the capsules empty beforehand. So there are ways of doing that. Harder to model vaccination as you go through. Yeah, that's complicated. So
yes, if you've got your playing cards, your aces and kings and queens could be vaccinated at some stage.
So if you pull them out, they don't infect anyone.
Yes. Okay.
They don't get infected, and they well, you've got some assumptions about what do vaccines actually do. Do they stop you getting infected? Do they stop you infecting others?
Okay.
Or do they just stop you getting very ill?
Okay.
You've got to take some decisions there.
Somebody's talked about we haven't taken into account people leaving the bag and newcomers arriving. Do we keep our airports open and let outsiders enter the population, or do we do what New Zealand did and close the airports and don't let anybody else? That kind of idea.
Well, what does the bag represent? Is it one room of people? Is it one country of people? So in epidemic modeling, we'd say that's a closed population, which literally means no one goes out the bag, no one comes into the bag. You can extend models, of course, to have throughput of people in some way, of course. It makes it more complex, of course. But,
yes.
Yes, that's a good one to spot.
Yes. Somebody's talked about different ages. So age factor, that maybe some people are more prone to be infected if they're not so healthy, perhaps, as maybe younger people, or maybe younger people are more prone.
Well, there could be proneness to infection, or age is also important for disease and who you mix with, right? So if you think about the children in your classes, they mostly are spending all day with kids of the same age, right? Maybe they're younger siblings, older siblings, but it's not random who you mix with by age, is it?
But we know that at the beginning of school terms, often, because children are mixing with so many other children, often everybody catches a cold, or has got flu, and teachers often get infected at the beginning of term because maybe they've led much more isolated lives during the holidays, and then all of a sudden they're exposed to hundreds of children.
Well, that's the R going from a small value to a big value suddenly as the term starts.
Okay, well, shall we look at the next model that we have an interactivity for, and to see whether we address any of the issues that have been raised, and see whether what extent we can satisfy those who'd like a more nuanced.
Right. So let's go back to the NRICH start of this.
Okay. So we've got 4 parts.
Mhm.
In the first one, we look at arithmetic and geometric progressions and make sure that students appreciate what happens when you double and double and double. And there's some examples, paper folding, for example, and the chess and the rice fable story, so that children begin to appreciate how things grow. And we've looked at the lucky dip in part 2. In part 3,
everybody is different.
Everybody's different.
This links into the age comment that we had. So we modeled everyone in that bucket of 26 that they're all the same. They're in the same place. They mix the same way. They get infected the same way. And age is one way to say it. Another way to say it is actually people live in different places, or people are in different places at work or whatever.
And the children who go to school are interacting in a very different way to somebody who's working in a context where they don't come across very many people.
So this gets straight onto that. So everybody's different. Oh, that's more me's. These videos are all pretty short, so they give you some of the explanation and narrative that we.
Yeah, they're just 1 or 2 minutes long usually.
So everyone has different interactivity. There's a key there. We're going to not read the instruction but compile in.
Yeah, we're going through this quite quickly to give everyone a flavour of what we've produced, but to whet your appetite and hope that you'll go and inevitably you'll have to read through the instructions and so on. Okay, so what have we got here, Julia? I can see lots of circles with zeros, white circles with 0, yellow circles with 1s, blue circles with 2. And on the scale at the bottom for R, I can see it's set at 1. Can we move it to the right a little bit? Maybe 2? Oh, we can do 2.2 or 2.1. Oh, so the request from somebody that we don't stick to integers.
We've got it here.
We've got it here.
There's a very cool thing that happens with this, actually. So it started on 1. I'm going to put it back to 1. If you look at the dots, I don't know if you can see them well on Zoom. I'm hoping you can. Well, it looks like you can get a sense of the colours there, even if you can't read the tiny numbers. The whites are 0s, the yellows are 1s, and blues are 2s, as Charlie said. If you choose another value, let's do 1.9. You see, it's mostly 2s and some 1s. So Oscar has done some clever backroom coding here, so that whatever R you choose, he makes it out of these.
So what does 2.1 look like? Mainly 2s with a few 3s?
Oh,
no
3s.
No 3s, but some 5s.
Yes, we go straight to the super spreaders.
Okay. So maybe the ones are, I don't know, people working on their tractors in farms and only coming across very few people. 2s are the majority of people, and then some 5s are teachers and nurses and people working in hospitals and people working in shops who come across a lot of people.
Yeah, or it could be biological super spreaders. So some people are just more or less infectious than others, right? Just by quirks of the biology.
Okay.
Some people cough a lot, right?
Okay.
or some people might be really, really, really careful, and even though there hasn't, they've got the same biological disease, their behaviour is different, so they don't infect as many people. Or it could be random, right? It's just chance of the day.
So what does this interactivity allow us to do? I can see that we can infect a random person, and presume we can infect more than one random person.
We can do that. So I'm going to click that once. So
yeah.
Just click that. Oh, there they are. I don't know if you can see them. I don't think you can see
like
my
a
cursor.
red, sparkly 2 there. Can we infect more than one person?
We can. The other cool thing you can do with this is you can choose who you're infecting.
Okay, well, why don't we infect a few 2s?
So I just do random? Or do you want to choose?
Well, I don't know. Maybe somewhere along the bottom, a 2 somewhere along the bottom.
Oh, infected, immune. So immune. So you wanted a model vaccination. There it is.
Okay.
So vulnerable. They already are vulnerable, so do nothing here. So let's infect them.
And another 2 somewhere here on the right.
Oh, where I am. Okay.
And
infect them.
okay, so we've infected 3 2s. So shall we run it and see what happens, and then maybe next time we'll infect 3 5s and see how that compares.
So generation, or just go for it, shall we, this time?
Go for it.
There it goes.
So they infect the people near them because they're those that they come across. And the R value is 2.1.
Do you know, I've worked in epidemics for over 20 years and I still find these things fascinating. Oh, it's still going? I think that's actually the end. There we go.
Okay.
Ooh.
So it's some little islands of people who weren't affected, but even among the part of the population which was heavily infected, there are still a few pockets of people that managed to.
I bet if that 5 got hit, all these other ones would have as well. So this one not getting, the chances are interlinked in an interesting way.
So this might have implication because you were one of the scientific advisors for the government during COVID. So models like this will have implications for who you choose to vaccinate, because if you know who the 5s are, and they're the super spreaders, I don't know whether that's the right way
it
to
is
refer,
the right word, yeah.
Then, and when we can't vaccinate everybody, either vaccinating them or asking them to stay at home. On the other hand, if nurses are the ones who are the 5s because they come across a lot of people, we can't ask them to stay at home because we need them in hospital.
You've just hit my main research question I'm working on still. Actually, there's in section 5, remember we've got those videos of the 4 researchers. I'm one of them, but it's 3 of my colleagues. What I'm talking about in that one is exactly this problem of vaccine allocation. So if you focus on this interactivity, okay, we're going to vaccinate the 5s. But if you think differently, well, hang on, some people get really ill with some diseases like COVID. You might want to prioritise vaccinating those people to protect them. And that would be right, in some sense. Or you have people like nurses, they're both in contact with more people, but you've also forced them by their job to do that in some sense. And maybe there's some ethical considerations. So you've got the ethical, you've got behavioural, you've got the infection. It's a really, really hard problem, but not one we can ignore because we have to make these actual decisions, or the government does.
And I know you've talked in the past about how your research is not just working with mathematicians, you've worked with people who know about transport, for example, and how people interact by having to go to work or move around and so on. And you are, did you say, Professor of Mathematical Biology? So you have also worked with medics and who understand
and vets.
Yeah, why vets? I was curious about this.
Do you know animals get diseases as well, right? So there's
But does the spread disease, is it different for animals to how it is from humans?
It depends what you're doing. So I mean, we're very focused on humans. In fact, for these resources, Contagious Maths, we're thinking about human epidemics. But of course, you get epidemics in animals such as farm animals that are interlinked with the human population, but also in wildlife, right? But even not just only animals, there's plant diseases as well, right? Of course. They're different. They don't.
We're going to need another webinar for this.
Yes, that's a whole different set of resources. But of course, that means we then work with plant sciences, we work with veterinary sciences, medical sciences, the virologists, the immunologists, of course. You want to know all this. Immunity is all in here, right?
But this is an issue that for school students, I mean, in particular, the sort of the philosophical, moral issues that you were talking about do not crop up very often in maths classrooms.
No.
And so hopefully these resources will introduce students to this.
I feel really strongly about that. I mean, in maths classrooms, sometimes it can seem there is the right answer and you get to it. And I know that's not true for what you do with NRICH. It's always got these high ceilings, but there's more you can do, ways you can think. But that's also true in research, right? We don't here is the answer. We've worked out the optimal vaccine allocation for every situation. It's really complicated, and there's lots of things to balance together. And there's always different ways to think about it. And that's the reality of what mathematics is like, whether it's applied maths or pure math. There's a lot more layers to it. It's not bang, I've done it, right answer.
Okay.
I'm aware,
I know that we want to show one more interactivity, but before we do, I'm just wondering, in the interactivity that we've just shown, we've managed to respond to some of the issues that were raised in the chat.
Yes.
Should we give everybody another minute to see what else they think?
Good idea.
How else would you want to improve on the latest model that we showed you, where not everybody has got a two? Some people have got ones and some people have got fives and some people have zero.
Got the mix, but it's also got the spatial arrangement. That's the other thing that's different. Whereas the capsules were all sort of in a jumble.
Right. So here you only infected the people who were very close to you.
Yeah, there's a sort of area around you can infect. So
okay, so
let's frame that into a question.
Is the question clear what we want people to write? Say in the chat.
Let's try and frame it. So now you've seen this model. What are the shortcomings of this model? And there are lots. Which ones are the ones that jump to your mind first about this? Would you use this to go and advise a government with? Maybe don't ask your class that. Or maybe do.
Yeah.
Brilliant. Yeah. That's okay, that's the really key one. So the comment is movement of people. Well, this would be a superb model for an orchard. If we're doing trees, but people don't sit next to the same people all day, every day. Well,
right.
Well, no.
And so we've got an interactivity, but you were slightly concerned that it might not show very well on Zoom.
Oh, no, I don't think it will, because it's the next level of this is indeed movement of people.
There is an intermediary there. If you go to the cog, we've got sort of, rather than the hexagonal grid, we've got suburbs and satellites. So shall we just look at that? And okay, so this seems slightly more realistic. People may be living in villages. Here in Cambridge, we have lots of villages that dotted around the fens around Cambridge, people coming into Cambridge, people going out.
Yeah, and I think this is one for teachers. Maybe think about how this fits with the context of where you are. Pretty much at any scale in the world, this will work, that there's a more major city, town, whatever it is nearby, or maybe you're in it, and there are more minor, so sort of suburbs around. We've got one vision of what that looks like for Cambridge. I'd think differently for London. I'd think differently if I was thinking about the whole of the south of England and different parts of the world, it might look different, but you can put a narrative and how this fits where you are.
So could we have an R value of 2.1, please?
You like this 2.1?
Well, just,
there it is.
And then could you immunize one person on each branch? So there's one of those, one. Yes. And
oh, I've got a little shield now. A vaccine's got the side effect of making you shield shaped.
So I hope everyone can see that. I'm asking, because it seems to me, again, thinking about vaccination, if we know who are these people who are connecting one group to the main city, can we stop the infection spreading from one community to another? And so then we're going to infect a few random people. I don't know.
Infect that one, and then maybe the right hand one.
Okay.
I think there's a chance of it getting through.
Yes.
Let's find out.
Shall we come on then?
Oh, it's jumped across through the side bits. It's gone round. Is it going to get into the middle though? It's got. Your strategy protected the city.
Right. I can see that this can be quite addictive. I can imagine wanting to play with this again. I mean,
you know, I don't click on this during the working day anymore.
but I mean, can you just say a little bit about how this reflects? I mean, you obviously work with more sophisticated models, but the way that we're seeing things happen as we make decisions about who's infected or who's vaccinated, and have a model that represents the real world in a more realistic way than the hexagonal grid or the lucky dip bag. Can you give us sort of a little bit of insight into what you're doing when you're at work and you're preparing to advise the government, for example?
I can. So there's a danger I'll sit here and click on this now unless I close the screen eventually. But when we are using a new model, a lot of us will just run it and change things and fiddle with it and get a feel for it, get an intuition for it. Not entirely unlike what we're doing now, actually. So this process of just maybe a not very organized exploratory approach, just trying, exploring what happens if. We might do that first, and then we might systematize a little bit. Actually, as we did with Lucky Dip, we said where we could actually log how many get infected each time, well, how many are left at the end of the epidemic. So we might then systematize a little bit more. And then the next layers of what we do look a bit different to this, because we're, got differential equation systems. We might be coming up with general results and then plotting it for, if we change the parameters, if R equals these different values, what's the output on this scale? So that's the kind of thing we'll be doing. And then we go back and find out what's wrong with the model for the purpose in hand. We maybe iterate the model a little bit. So that processing.
And finding out about what's wrong with the model is, to what extent does that model reflect what's happening in the world out there? Is that right? How do you work out whether the model, how accurate the model is, how well it represents what's really happening?
So during a live unfolding, it's very different to sort of research normally. We don't start thinking, oh, how do we do modelling of infectious disease? We've had 100 years to think about that. We might start with a set of models for the UK, and I'll give you an example. To start with, we didn't have vaccination in there because there wasn't vaccination. As the vaccines are developed, we start to build it into the models, knowing what we know about the vaccinations. As different variants appeared, we had to add those variants in the simulations here. We've just got one disease, thankfully. But then you might have two different variants interacting, and the immunity for one maybe does it work for the other or not? And you have these questions. And then the side we don't have here is we are dealing with real data. So if we start getting a better or different data stream, maybe we get to know cases down to a finer scale. A model to be spatial down to a final scale, because it's worth modelling that because we can fit it to something now that we have the data.
And presumably you'll need different models for different populations, because different people in different populations behave differently and working in different contexts and
types,
or villages, or sort of the countryside and cities will interact in different ways and come across people.
And sometimes the same model actually works surprisingly across different contexts as well. So it's not always as different as you think it's going to be.
And so when you were advising the government, were there other people who had slightly different models also advising, and you were to tell us a little bit about that?
It wasn't just one group of modelers sitting in a room somewhere. Of course, we're all sitting in a gazillion different places. There were hundreds of us working. And I would say for the given fitting of the current R, which we tried to work out what it was by fitting and then predicting a little bit on, I think there was typically about 14 or 15 different modelling teams running, and each of those teams running their own type of models. So we then had to merge those together, and there wasn't one which was right and wrong. They're all different. So they all gave different insights, and then you have interesting discussions where one is a bit different to the others. You say, what? You don't say, you're wrong.
No.
You say, what have you done differently to the rest of us this week? What have you done differently? And do we learn something from it? Is there something, okay, this presents as the insight, this is what might happen in the future if, or in fact, there's something we're all missing now.
And did you find that sort of the average of all the models was more or less, was more accurate, actually added to the accuracy that...
It always does.
Yeah.
It always does, the wisdom of crowds.
Yes.
But even more value than just the average was the discussion about the distribution around, this discussion about why your model is different to mine this week. Learning from that sort of diversity of approaches was far more valuable in taking, say we just submit it, we don't talk, we just take the average. That wouldn't have been as useful.
Okay.
So some of these discussions amongst the modelers, which got very nerdy sometimes, and the details of, well, I've coded up this way with this step size and this, and it's like, okay.
And presumably the work continues now. There's the Juniper Group, is that?
So the Juniper Consortium, which is working very closely with Plus, actually, so we continue to communicate our research as it happens.
So my impression is this is very different to sort of the stereotypical view of mathematicians where maths is sort of very accurate and logical, and this is much messier than when at school we're solving some intelligence equations or something of the sort. And that was one of the messages that you perhaps wanted students to take away, that there is a lot of sort of trying things out and improving and testing ideas. Do you want to say a little bit about that?
Yeah, I mean, on the one hand, it's frustrating. You just want there to be, okay, I do the simultaneous equation, x equals this, right, I'm done.
Yeah, that's what I like about maths.
And then the other side is, hang on, okay, this is not so clear cut. There isn't a right and wrong. That's annoying. But wait, this is interesting. There's something intriguing about this. I want to know more about this, but what if? And hang on, there's another layer of interestingness. So you know, the frustration of the single answer being right, you can put that aside pretty quick if the problem itself is interesting. And for me, particularly the applied maths problems, okay, I know what we've got on screen is not the same thing as a real epidemic, but I'm learning something about real epidemics at the same time by building the intuition. So connecting all these things up, yeah, you know, maths isn't on its own, it's interconnected to all these ideas. It's messy, it's complex, but that makes it more interesting.
Even though we might not want to run the interactivity of part 4, which I think is called Get Moving.
There it is.
I mean, can we just look at it just so that, and we have cogs and we've got, different settings. So a party where people are sort of milling around and chatting or dancing with different people.
This is party mode. Let's keep that actually.
But you also have visitors, and you've got commuting.
Yep.
Where people move from the suburbs perhaps to the city and back, and some people stay at home and some work from home and others don't. Are you saying that if we run this,
some people were infected? I think it doesn't come across as clearly on Zoom because it doesn't stream video.
Okay, but
but
there is some movement going on. People are interacting, and then at some stage stopping, and we can see the effect of people being infected and infecting others.
Actually, someone in the first time we asked for questions said about time, the fact that we had generation 1, generation 2. This has got now a more continuous time. And the little bars, like almost like health bars, but they're time bars for how long the person has until the end of their infection. That's also in this one.
Okay, so this again is a more nuanced model than the original lucky dip that we had.
But you might notice already it becomes harder to analyze it.
Yes.
So complexity, good, because it represents reality better, but harder to extract some general.
But that's why we need people like you who are prepared to
the simple one.
I'm aware of the time, Julia. Are there
maybe in 30 seconds, maybe you can say something. I know we've got some people here who haven't engaged with NRICH before or heard of NRICH.
Well, do you want to first of all go to the resources? Oh yes, well, we've got them here. If we go back to the very first,
I'm going to go back to here and go back in again. Yeah.
Okay, so oh no, I meant the one before, please.
This page itself.
Yeah, this is the introductory page. Just underneath the video, we've got a link where on the right here, lesson by lesson breakdown.
Yes.
Which draws attention to the different parts. So we've produced 4 parts and a 5th one, which is the wrap up and meet the researchers.
Yeah.
And here I've also added this in italics, asking for feedback from schools.
Perfect.
So anybody who uses these resources, we've had some feedback at the pilot phase. But now that we're releasing these resources, it'd be really nice to hear from teachers who are using the resources. And if we scroll down, for each part, we've put it sort of sketched out sort of what happens at the beginning and the middle and towards the end of each part. What are the key questions, curriculum links and so on, and links to that. And this is in the style of enriched problems. For those who don't know very much about NRICH, I suppose, yes. Goodness, I'm being put on the spot here to say something quick. I suppose what is special about NRICH is NRICH tasks that we publish is that we often start by offering a challenge and starting with a problem without demonstrating how to solve problems of that sort. So the idea is we start with the problem and then build on students' ideas, and the problems that we publish have got teachers' resources. Liz's appeared on screen. She can do a much better job of describing.
So, Liz, do you want to? So Charlie, you're the secondary coordinator.
Yes.
So, and Liz is for primary. Do you want to introduce yourself?
Hi everyone, yes, my name's Liz and I'm the primary coordinator of NRICH. So my role is very similar to Charlie, although I look after the content that we create, which is great for children from the age of 3 or 4 up to 11 or so.
And Julia was asking us to, in a sentence capture what the essence of what we try and do at NRICH in terms of the kind of problems that we publish.
Yeah, well, I mean, I'm not sure I would say anything differently to what you've said, Charlie. It's about giving children the opportunity to think and work like a mathematician. So we're offering tasks that are genuinely problems, so they get to experience all those phases of problem solving, but with the support of you, their teachers.
Yeah.
Brilliant.
Thank you, Liz. Julia, we've only got a minute, I suppose. We started 2 minutes late, so we'll finish 2 minutes. Do you want to just final messages about the resources that we've produced and the messages you're hoping students will take away with from working on these resources?
Yeah, I hope you share our enthusiasm for engaging with epidemics and using that to explore mathematics. This whole project of linking together what we're doing with NRICH and Plus and with research is a new way of doing things. Really value your feedback to hear what you make of it, what works well, what doesn't, and give us tips for the future. But we hope this works brilliantly for you as well. So thank you all for engaging with this.
And thank you very much for offering to join us for this webinar.
Absolute joy.
Great.
Right.
Thank you. Bye-bye, everybody.
Thanks, everyone.